Okay, so how do we get a most efficient preparative chromatographic separations? And the magic and the secret of that lies in the efficiency of the particles we are using. So what you see here is a drawing of a few particles. And the particles in preparative chromatography we are using, they typically have a diameter, a particle diameter of between 10 and 100 micrometer. And because we need most surface area, we need a high surface area to have a lot of adsorption places, most of the particles we are using in preparative chromatography, they are porous. They are totally porous. And the porosity is something which has to be adjusted to the compounds we want to separate. Imagine a very large compound to be separated, which is introduced into our chromatographic system, but is not able to enter the pore system. So this will go through the extra particle volume and will come out of our chromatographic column quite soon. So then we have something which eludes here with T0, the column dead time we already learned in the first part of our video. The smaller particles, the smaller compounds to be separated, they will be also transported by convection, so by the flow which our pump is delivering, but they are able to penetrate into our pore system. And here's something very important happens. Up to this point, we have convection. So the faster our pump is pushing the mobile phase through our column, the faster our compounds travel. As soon as the compounds enters the pore system, it's transported solely by diffusion. And diffusion is much slower compared to convection. So this takes a long time for our relatively long time for our compound to travel along the pore system. And then we have to design something which is the discriminating part between the separation of different compounds. So here we have the adsorption of one of our compounds to the surface area. When we change the mobile phase, or after a certain amount of mobile phases pass through the column, we have the desorption of our compound again, and it's transported by diffusion back to the outlet of the particle and is then transported out of the column. So at that point, we see this compound coming out and we can detect it. And we already know that this is the retention time of this compound here, T1. And now we have a look to this peak shape we have here. And for that, we divide our peak into two parts, and we look here at 10% of the height of the peak. And we see that the two parts of our peak, A and B, are not equal. And this is something which is summarized by what is called the asymmetry of a peak, AS. And AS is simply B divided by A. So if both parts of the chromatogram are the same, B equals A, we have an asymmetry of 1. And the value of 1 is the most perfect value of a well-packed column where we don't have these, what is called tailing effect. The longer the tailing effect, and it comes from not well-packed columns, or it comes from the adsorption and desorption characteristic in the beads, the more problematic it is to separate more than one compound in our chromatogram. And remember, from the first part of our video, we collect from here to here. So the more asymmetric the peak is, the longer is this collection time, the higher is the dilution, and the more volume we have to process in the next step. So far, we have only looked into one peak. And now we really go to a separation. So we introduce a second peak, which is well separated from our first peak. It has a retention time which is now called T2. And to characterize the separation, how well separated these two compounds are, we introduced alpha, which is called the selectivity. And alpha is K'2 of the retention factor of the second peak divided by K'1. Reminder, K' is calculated T1 minus T0 divided by T0. So if K'2 and 1 are the same, we have a complete overlapping of our peaks, we have an alpha value of 1, and we have no separation. So to have a separation, we need an alpha value which is greater than 1, and that means that our K' has to be higher, K'2 has to be higher than K'1. When we have this situation, we can separate peak A, the first peak, and the second peak with both 100% yield and 100% purity, which is ideal. In preparative chromatography, that is our ultimate goal. We would like to have as much material as possible with a maximum purity. But this ideal chromatogram is not what you see often in reality. So often in reality, you have a separation which looks more like this. First compound, second compound. Very poor separation, so no complete resolution. And resolution is what is counting in preparative chromatography. And resolution is defined as the distance between the two peaks. So if we have a separation which is just baseline here, so our UV signal goes back to baseline and then the second peak appears, then resolution equals 1.5. The optimization of resolution is the most important point in preparative chromatography, because we want not to have these overlapping areas here where we don't have sufficient purity, so we have to cut fractions, we lose yield. So because of that, we will now optimize our resolution. And resolution, the equation for resolution, has three main factors. The first one is related to alpha, the selectivity. The second term is related to K', and the third term is taking into account the efficiency. So now how can we optimize our resolution? In principle, we can increase all these three parameters. We can increase selectivity, we can increase retention, and we can increase efficiency. The most important one, or the one which has a lot of drawbacks, is to increase the retention. If we just increase the retention of our chromatogram, we need a longer time, we have a longer cycle time, we need more mobile phase, and because of the diffusion, we broaden our peaks. So in principle, what we should optimize is efficiency and is selectivity. If we optimize efficiency, it will end in two peaks, which still have the same retention times. So our peaks appear at the same part in the chromatogram. The only thing which is different is that the peak width is narrower. And with that, we have now the possibility to separate again both peaks in 100% yield and 100% purity. So how do we optimize efficiency? First of all, we pack our column as careful as possible. Second is we take a sorbent which has very limited distribution of the particles. Then we need a material where adsorption and desorption is taking place fast. That is, for example, what we do with our tentacle technology, which we use for Fractogel and Eschmuno, where we have a very fast desorption characteristic. Last but not least, to increase efficiency, you can go to smaller particle sizes. But have in mind, when you go to smaller particle sizes, the smaller your particle, the higher the pressure drop of your chromatographic column. So this has a certain limitation. What is without limitation is to increase selectivity. When we increase selectivity, the peak width stays the same, so not very efficient peaks. Let's say T1 stays the same, but T2 is now longer because we have increased the selectivity, and increasing the selectivity in this case means the attraction forces for our second compound of interest is higher than it was in the original chromatogram. So if we increase the selectivity, it's the best way to optimize our preparative separation. And how we put that all into a chromatographic system and into a complete chromatographic separation cycle, we will have a look to that in the third part of our video.